Section 8.5 Ratio and Root Test. In this section, we develop two additional tests, the ratio test and the root test. These tests apply only for series with positive terms. You can imagine that a series of positive terms sigma ak converge if and only if the sequence ak decreases rapidly enough towards zeros. One way to measure the rate at which the sequence ak is decreasing is to examine the ratio ak plus 1 divided by ak as k grows large. This approach leads to the following result. Ratio test. Given the series sigma ak with ak positive and the limit ak plus 1 divided by ak is L when k becomes large, the ratio test states the following. If L is less than 1, then sigma ak converges. If L is greater than 1, then sigma ak diverges. If L is 1, then the test is inconclusive. It means that you have to try another test. We take an example. The geometric series sigma k equal 2 to infinity of 1/3 to the power of k converges because the absolute value of r equals 1/3, which is less than 1. Let's try the ratio test with this series. First, we compute the limit ak plus 1 divided by ak when k tends to infinity. The kth term is 1/3 to the power of k, and the k plus 1 term is 1/3 to the power of k plus 1. So the ratio is 1/3, and the limit is also 1/3. Thus, L is less than 1, and the ratio test tells us that the given series converges. So, how can we understand the ratio test? This test is in fact a generalization of the simple test for geometric series. In geometric series, the ratio ak plus 1 divided by ak is a fixed number r, and the geometric series converges if and only if the absolute value of r is less than 1. In more complex series, the ratio ak plus 1 divided by ak may not be fixed, but in the limit tends towards a fixed value. The rules are similar. If the quotient approaches a value less than 1, the series converges, whereas if it approaches a value greater than 1, the series diverges. You will find the ratio test most useful with series involving factorials or exponentials. To show that the test fails if L equals 1, it is enough to consider two series. The first series is sigma 1 divided by k plus 4. The term ak plus 1 equals 1 divided by k minus. The term ak plus 1 equals 1 divided by a. The term ak plus 1 equals 1 divided by k plus 5, and ak equals 1 divided by k plus 4. So the ratio is k plus 4 divided by k plus 5, and the limit of which is 1. In this case, the ratio test is inconclusive. However, by limit comparison test with the harmonic series sigma 1 divided by k, we know that it diverges. The second series is sigma 1 divided by k squared plus 4. The term ak plus 1 equals 1 divided by k plus 1 squared plus 4 and ak equals 1 divided by k squared plus 4. So the ratio is k squared plus 4 divided by k plus 1 squared plus 4, and the limit of which is 1. In this case, the ratio test is inconclusive. However, by limit comparison test with the p-series sigma 1 divided by k squared, we know that it diverges. However, by limit comparison test with the p-series sigma 1 divided by k squared, we know that it converges. We have seen that when the ratio ak plus 1 divided by ak tends to 1, the series may converge or diverge. In those cases, we should try another test. Let's take a look at some more examples. Test the series sigma 3 to the power of k divided by k plus 2 factorial for conversions. Let ak be 3 to the power of k divided by k plus 2 factorial, then ak plus 1 equals 3 to the power of k plus 1 divided by k plus 3 factorial. The ratio ak plus 1 divided by ak equals to 3 to the power of k plus 1 divided by k plus 3 factorial multiplied by k plus 2 factorial divided by 3 to the power of k. Express the factorials and reduce the common terms. We are left with 3 divided by k plus 3, the limit of which is 0. Thus, L is less than 1, and the ratio test tells us that the given series converges. The next example is a little bit more challenging. Test the series sigma k to the power of k divided by k factorial for convergence. Let ak equals k to the power of k divided by k factorial. Then the ratio ak plus 1 divided by ak equals to k plus 1 to the power of k plus 1 divided by k plus 1 factorial multiplied by k factorial divided by k to the power of k. Express the factorials and reduce the common terms. We are left with k plus 1 to the power of k divided by k to the power of k, which can be written as k plus 1 divided by k to the power of k, or 1 plus 1 or 1 plus 1 divided by k to the power of k. Recall that the limit of this equals to the number e. Thus, L is greater than 1, and the ratio test tells us that the given series diverges. In the following example, we investigate the conversions of a series of power functions. For all numbers x greater than 0, so that the series sigma k cubed multiplied by x to the power of k converge. This is called a power series and will be discussed in more detail in sections 8.7 and 8.8. Viewing x as fixed, we apply the ratio test. The limit ak plus 1 divided by ak equals to lim of k plus 1 cubed of k plus 1 cubed divided by k cubed multiplied by x, which equals to x. So the given series converges if the limit x is less than 1, and diverges if x is greater than 1. When x equals 1, the ratio test is inconclusive, so we must change this case separately. When x equals 1, the series becomes sigma k cubed, which diverges by the divergence test. So, the values of x for which the given series converges is the half-open interval 0, 1. We take another example of a power series. Find all number x so that the series sigma k cubed multiplied by the absolute value of x minus 5 to the power of k converge. We try the ratio test. The limit ak plus 1 divided by ak equals to k plus 1 cubed multiplied by the absolute value of x minus 5 to the power of k plus 1 divided by k cubed divided by the absolute value of x minus 5 to the power of k, which yields the absolute value of x minus 5. The series converges when this limit is less than 1. Solving the absolute value of x minus 5 less than 1 gives x greater than 4 and less than 6. The series converges for all x greater than 4 and less than 6. When x equals 4 or x equals 6, the series becomes sigma k cubed, which diverges by the divergence test. So, the values of x for which the given series converges is the open interval from 4 to 6. The next test is the root test. This test is in fact a generalization of the divergence test. In the divergence test, we simply compute the limit of the sequence ak and observe whether that limit is 0. Unfortunately, most interesting series have lim ak equals 0, so the divergence test cannot be used. However, the following result shows that it may be possible to say more about the convergence of sigma ak by examining what happens to the kth root of ak as k becomes large. Given the series sigma ak with k positive, given the series sigma ak with ak positive, and the limit of the kth root of ak is L when k becomes large, the root test states the following. If L is less than 1, then sigma ak converges. If L is greater than 1, then sigma ak diverges. If L is 1, then the test is inconclusive. It means that you have to try another test. As you will see in the following example, this test is particularly useful with a series involving a kth power. Test the series sigma 3 to the power of minus k multiplied by k to the power of k for convergence. We try the root test. Let ak equals 3 to the power of minus k multiplied by k to the power of k. Then the kth root of ak is k divided by 3. When k tends to infinity, the limit is infinity. Since L is greater than 1, the root test tells us that the given series diverges. We take another example. Test the series sigma k squared divided by 2 to the power of k for convergence. Let ak be k squared divided by 2 to the power of k. Then the kth root of ak is the kth root of k squared divided by 2. Remember that lim of the kth root of k when k tends to infinity equals 1. So the limit is 1/2. Since L is less than 1, the root test tells us that the given series converges. This is the end of section 8.5. Thanks for watching.